So today I'll talk on localization and its application. So we discuss uh, the main thing we will discuss the formation of rings of fractions. In modern language we call it localization, and also we'll discuss modules of fractions. Okay. So this associated process of forming rings of fractions and modules of fractions we call it localization. So this is called. So we'll start with a simple example, that is basic example, that forming field of rational numbers from the ring of integers. Okay, so this we start with this example. The formation of Q, that the field of from Z, that is nothing but the ring of integers, and then we will see that how this notion can be generalized easily to integral domain. Okay, and further we'll study what we call localization or ring of fractions. Okay, so let's recall how an element of Q looks like. So an element of, so a rational number, it looks like, so we generally write in this way, a by b, right, for some integers a b belongs to z, such that this b is non-zero. That is the only condition we have. Now you note that though it is simple, but we should note it to understand this notion better. You can write this 1 by 2 in many ways, right? So for example, it is same as 3 by 6, and that is same as let's say 4 by 8. Okay, so what is this number then? So in general, if we consider two rational numbers a by b and c by d, so they are same if and only if this ad, that is same as bc. So basically, thus this number a by b, it can be, yeah, so it can be thought as the equivalence class of this pair a comma b belongs to, so first component is coming from z and second one is coming from z star. So where this z star is nothing but collection of all non-zero integers. Okay, consider this one with respect to the relation. This is the relation if and only AB equal to BC. So whenever you have some questions or doubts, you just stop me and you can ask. In that way, it will be more clear, I think. And yeah. So this rational number a by b, we can think it as equivalence class of this pair a comma b, where this first component it can be any integer, and the second component it is just a non-zero integer. Okay, with respect to this relation. In fact, this relation we can verify that it is an equivalence relation, and with respect to this relation, this A by B, that is the notation we are using to denote a rational number, it is nothing but an equivalence class of this pair. Okay, so just like this number, it is equivalence class of this pair. In fact, you have other representative also. Let's say 3, 6, right? And then this addition and multiplication of these equivalence classes, this can be defined by considering any representative in the obvious way. So we know how we can add two rational numbers and how we can multiply two rational numbers, right? And we can see that that addition and multiplication, it is independent of the choice of the representatives of this equivalence class. So for example, this rational number, it is nothing but the equivalence class of this thing. So you have other representative also. But in addition and multiplication, you may use other representative, then also you will get same number, same equivalence class. Okay. So this is the basic example to understand field of fractions or ring of fractions. Okay. So one can generalize this notion to any integral domain and construct field of fractions for an integral domain. So more generally, we can generalize this thing. Okay. More generally, we construct. So here you observe that to get Q from Z, we are actually inverting all non-zero elements. So elements in this set, right? And so in the denominator, you have all non-zero. You can have all non-zero elements. So basically, you are inverting all non-zero elements. So whenever B is non-zero, you can have its inverse, that is 1 by B. Okay. In that sense, you are just inverting all non-zero elements of Z to get this field of rational numbers Q. Okay. So here we construct ring of fractions. We denote it in this way: S inverse R by inverting the elements in a subset S of R. So here we should take this R, it should be, yeah. Okay, so here I should, right? We will generalize this notion to define ring of fractions. Okay. So throughout this is my assumption. Throughout R is a commutative ring with identity. So now one may ask whether localization exists for non-commutative ring or not. I'll say yes, but then this theory is difficult. Okay, so let's assume commutative ring and see what is localization or ring of fractions. So this is my assumption, or now we will construct ring of fractions S inverse R by inverting the elements in a subset S of R. And what kind of subset is this? So what kind of subset is this? So it is not any arbitrary subset, but we should consider. Okay, so we should we should consider a special subset, namely multiplicatively closed subset. Okay, and why we need to consider this multiplicatively closed subset, it will be clear once we define this ring of fractions. Okay, so this is the notation actually. So starting with a commutative ring with identity, you consider a multiplicatively closed subset, and what we are doing to construct this S inverse R, basically we will be inverting all the elements of S. Okay, to construct this ring of fractions. So that is why we denote in this way S inverse R. So basically we are inverting all elements of S. So just like here we have inverted all non-zero elements, all non-zero integers to get Q. Is it fine? Okay, so now let's first define what is multiplicatively closed subset. So this is the definition. Okay. A multiplicatively closed subset of R is a subset is of R which satisfies these two properties. Okay. First one is the S should contain that identity, multiplicative identity of the ring. Okay, and from the name it is clear it is multiplicatively closed. So whenever you have two elements in S, then their product that is also there in S. Okay, and then we will see the formation of ring of fractions S inverse R from R. Okay. Okay, so you just recall that example, that is the formation of field of rational numbers from the ring of integers. So here also we just considered this relation. So you first define a relation on this this set of direct product. So it is a Cartesian product, I should say. So it is R Cartesian product with S, and we define this relation on this set by if we have two ordered pairs. So then they are related if and only if you have U times. So you may simply write this one that if and only if, so these two ordered pairs are related if and only if T times. So you just think in this way, A by S that is same as B by T. So you may think that it should be we have equality here if and only if this T times A that is same as S times B. But if you define in this way for arbitrary rings and for arbitrary multiplicatively closed subset, then this relation it is not an equivalence relation. Okay, to make it equivalence relation, we define this relation in this way that U times T times A minus S times B, that is 0 for some U belongs to S. Okay, and why we need this condition, that will be clear if you try to prove this condition, this one, that this relation, this is an equivalence relation. Okay, it is reflexive. Reflexive you can clearly verify. Of course, it is symmetric. That also can be observed easily. And you need to prove that it is also transitive. Okay, to prove it transitivity, to prove this transitivity, you need this condition. Okay, it will simply define that these two ordered pairs are related if and only if just this thing is 0, then it is no longer transitive. Okay, to make it transitive, you need to multiply by some element of S. Is it fine? So let me know if you have any question or any doubts. Yeah. So then we have defined a relation on this set, and it is an equivalence relation. So we can consider equivalence class of every ordered pair. Okay. So then this equivalence class we can denote the equivalence class of this ordered pair A comma B by, okay, so I should do A comma S, this is by A by S. Okay, so this is just notation, I should say. Okay, so you have this commutative ring with identity. Now we are forming another ring, and that we call ring of fractions. So how we are forming that ring of fractions? So we are just trying to invert all elements of S. Okay, so this is the way. So you have this equivalence relation, and then this equivalence class of this ordered pair you denote in this way, A by S. Okay, and then you set this set we define in this way. This is just collection of all equivalence classes. Okay, so this is the equivalence class of this ordered pair. So it is coming from R cross S. Okay. Now we want to give a ring structure to this set. Okay, how? In the obvious way. So we a ring structure on S inverse R by defining. So you consider two elements in this set. Okay, that means two equivalent classes. One is A by S, another one is B by T. So how can we add them? So in the obvious way. So you just recall addition of two rational numbers. Okay, so let's define in that way. So denominator you will have S times T, and it is T times A plus S times B. So everything is happening inside R. Okay, so this sum, this multiplication T times A plus S times B, it makes sense, right? You have addition and multiplication in that ring R. Okay, so you have this element, and what about this S times T? So it should be an element of S, right? S and T both are coming from S, so their product that is also there in S. So that is the reason we have considered a multiplicatively closed subset. Okay, and you have, so you can multiply these two numbers in this way. It is A times B, and in the denominator you have S times T. Okay, so you can verify that these definitions, these are well defined. What I mean by well definedness, so whenever you have equivalent class, you should verify this well definedness, because for every equivalent class you can have many representatives, right? But whatever you are defining, whatever object you are getting, you should verify that it is independent of the choice of the representatives. Okay, so you can verify that. Okay, is it fine? So with these operations, S inverse R is a commutative ring with identity. Okay, and this is called is called the ring of fractions. Or localization. Why we call it localization, I'll explain it later. Okay, so this is localization of R at S. So basically we are inverting all these elements of S to get this ring of fractions. Okay, so I said that this is a commutative ring with identity. Can anyone tell me what should be the identity element of this ring? Anyone? Yes? I'll be happy to get a response. Yes? So let me know whether you are following or not. So we have constructed a set. So starting from a commutative ring with identity, we have constructed this set and we have given a ring structure by defining this addition and multiplication. Of course, you should verify that these two operations are giving a ring structure on this set, and that ring we call a ring of fractions or localization of R at S. Yes. So can anyone tell me that what is the identity element of S inverse R? Can you hear me?
One by one is the identity.
Okay. So do you have any other representative? Okay. I'm very happy to get this. So this is so an identity element of course, whenever you have identity element and that is unique, so I should write the identity element of S inverse R. This is of course 1 by 1. Now, do you have any other representative? So this is an equivalence class, right? So do you have any other representative? Let me know whether you have understood or not. Yes?
Any
Okay.
unit by unit.
No need to consider any unit. So you can consider any element of S actually. For any element, okay. For any element S. Yes. Okay. Okay. So the zero element. Okay. So this is okay. So now onwards, this element I will write this in short to save time. So the zero element of S inverse R. Can anyone guess? Of course, you can say that it is 0 by 1. Okay, and you can have 0 by S also. For any S belongs to S. Now, you can tell me, so with respect to this relation, you just consider an arbitrary element. So this is remarks. I should, okay, yeah. I have these remarks. First one, that you consider an arbitrary element in S inverse R. Okay, so now when it is a zero element, when it is the zero element of S inverse R. So zero element you have this representative 0 by 1. Can you tell me when this A by S it is the zero element. Yes, just from this definition, can you guess? Can you guess? Okay, so this is A by S is the zero element if and only if there exists some t such that t times A equal to 0 for some t belongs to S. Okay, so I think okay, so let's just see this special case that when this is an integral domain, is an integral domain, sample given that you just consider this ring of integers, okay, and S this is R minus 0. Okay, by the way, so is this set a multiplicatively closed subset of R? Can anyone tell me? If yes, then what is this S inverse R? So in that case, so for let's say you just consider this Z ring of integers, and S is the collection of all non-zero integers. Is it a multiplicatively closed subset? Of course, yes. So you just consider two non-zero integers A and B, then their product that is also non-zero, right? So same thing holds true for an integral domain. So for an integral domain, this is a multiplicatively closed subset, and of course, then you can form this ring of integers, and in this case, it forms, it gives a field, and that is called which is called the field of fractions. Field of fractions, and it is denoted by, we denote in itself Q of R. Okay. So field of fractions of Z, that is just Q. Field of rational numbers, right? Okay. Now you may think that what is the relation between R and S inverse R? So you have this natural map. The natural map, let me denote this by F, okay, from R to S inverse R. So can you give a can you define a natural map from R to S inverse R? Yeah. So if A is an element, then what should be its image? Can you get an element of S inverse R in a natural way from A? Yes, anyone? So what about A by 1? Okay, now you have a map, and now if I ask you whether this map is a ring homomorphism or not, what is your answer? Is it a ring homomorphism? So you can verify that this is a ring homomorphism because it preserves both addition and multiplication. The way we have defined addition and multiplication here, uh, it, it, it yeah, it shows that this natural map is a ring homomorphism. Okay. Now one may ask that whether this ring homomorphism, this is injective ring homomorphism or not. So what is your answer? In general, yes. Is it injective? Okay, so in case of Z, if you consider Z and S is just all non-zero integers, then of course you are getting a field, and in that case you can verify that this is injective ring homomorphism because A by 1, that is 0, if and only if there exists some T this is 0 for some t belongs to S, right? But t times A equal to 0, that does not imply that A is 0, right? So this thing you have, okay. So I can give a condition. You can verify that it need not be injective in general. However, this F is injective. You can only consist of okay. Okay, maybe you can verify this. So F is injective if S consists of non-zero divisors, or every element of S is a non-zero divisor. Okay, right. Okay, so in general this map is not injective. Okay, but when your this ring R is an integral domain, of course in that case every element of S is a non-zero divisor, and in that case it is injective. So you can see that when R is integral domain, of course you are when S is this collection of all non-zero elements, you are getting a field, and that field will contain R as a subring. Okay, so in that way every integral domain that can be extended in a field, and that we denote Q of R, and that we call field of fractions. Okay, and this Q of R, it is containing R as a subring. Okay, now let's see some more properties of this localization. This is 4. So this is the universal property. Okay, this is the universal property of ring of action. Okay, so you consider two rings A and B. This is a ring homomorphism. It's a ring homomorphism, and this S, this is a multiplicatively closed subset. Okay, and you have this condition that this G of S, this is okay, this is a unit for every S belongs to S. Then okay, this is number 1. Then there exists a unique ring homomorphism such that this H composed F, it is actually G. What is F? So F is that natural ring homomorphism A to S inverse A. A goes to A by 1. Okay. So this is the universal property. Even we can define this localization or ring of fractions in terms of this universal property. Okay. That whenever you have a ring homomorphism from this A to some other ring B, and S is a multiplicatively closed subset of S, and you have this condition that every element of S, it is actually mapping to a unit. Okay, then there exists a unique ring homomorphism from S inverse A to B. Even this unique ring homomorphism, that will be an isomorphism provided you have these two extra conditions. This is statement 2. Furthermore, if this is 0, implies S times A equal to 0 for some S belongs to F, and every element B belongs to B is of the form G of A times G of S inverse for some S belongs to S and A belongs to A, then there exists, this is the notation for there exists a unique isomorphism. In this case, H is isomorphism from S inverse A to B such that H compose F, this is equal to G. Okay. Yeah. Now we should see some examples. So here are some examples of okay. So first one. So throughout we have this assumption that R is a commutative ring with identity. Okay. So you just consider R and S, that is the singleton set consisting of only identity. So you need this condition, right? That multiplicative identity should be there in S. So this is the simplest possible multiplicatively closed subset, right? So in this case, what is S inverse R? Can anyone tell me? What is S inverse R? You are just inverting one. What is S inverse R? Yes. It is R only. So you can say that this is isomorphic to, okay, now this one, that, okay, so you just consider an element of R, okay, and then S is this one, 1 R, R square, cube. So is it a multiplicatively closed subset? Of course, this is a multiplicatively closed subset. Yeah. Okay, and then this S inverse M, it is denoted by this M suffix R, and we call it okay. So here we have not defined what is module of fraction, so let's just consider this S inverse R. So this thing we denote in this way, R suffix R, and call the localization of R at the element R. Okay. Yeah. So let's fix two notation. This, I think you are familiar with this. This spec of R. It is okay. So it is collection of all prime ideals of R. We denote by spec of R, and so we just max of R or max spec of R. That is just all maximal ideals of R. Okay. So then you can have the third example, that you just consider okay, the prime ideal. Okay, and now in a natural way, can you construct a multiplicatively closed subset? Then this S R minus P, that is collection of all elements of R, and that is outside P. Of course, this is a multiplicatively this is multiplicatively closed subset. Okay, and then this S inverse R. Okay, it is denoted by this R suffix P, because this localization, this ring of fractions, it depends on P, so we denote in this way. Okay, and we call it localization of R at the prime ideal P. Okay. The fourth one, it is a special case of these 2 and 3. You just consider this ring of integers, and you have, let's say you have this prime number. So this is prime number. Okay, so in 2 we have this localization at an element R. So in this case, you can consider, so, and we have denoted this by Z suffix P. Can anyone tell me how an element of ZP looks like? Yes. So here we are inverting all powers of P, including 1. Yeah. So an element of ZP, how does it look like? Can anyone tell me? Yes. So this is A by P power N. Of course, this A coming from Z, it can be any integer, and N that is greater than or equal to 0. Okay, and of course N is, okay, I can write in this way, that it belongs to, so it is any non-negative integer. Okay, when N is 0, then P power N, that is 1. So yeah, in the denominator you can have all possibility. So here R is P. Is it fine? Okay, now for this prime number P, you can have a prime ideal. So this is there in spec of Z. Okay, so this thing, okay, and this is, we denote this ideal generated by P. So now if I just write this one, an element of Z localized at this prime ideal, how does it look like? Can anyone tell me? Yes, it is A by S. And what should be the condition on S?
P shouldn't divide S.
Exactly. So S should not be there in this prime ideal. Okay, ideal generated by P. So P should not divide S. Okay, so these are two different notations, and so, and in fact these two examples are most familiar examples that we use in localization. Okay, and it has so, and they have many applications. Okay. Okay, so now let's see what are these ideals of localization. Okay, and then we'll see module of fractions, and then finally we'll see some applications of localization. Okay, so this is the proposition, and this is ideals of localization. So you consider a ring of fractions. So S, this is multiplicatively closed subset of R, and F is this natural ring homomorphism. Okay, so here A goes to A by 1. Yeah, is a ring homomorphism. Now one may ask that an ideal of S inverse R, how does it look like? Okay, So, okay, now first observe that for every ideal, I of R, can you construct an ideal of S inverse R? Okay, what about its extension? Via this map F. So this extension via F. It is given by. You can verify this is just this set. We denote in this way S inverse I, and because it is just collection of all A by S, where A is coming from I and S is coming from S. So this is nothing but the ideal generated by image of I via this map. Is it fine? So for every ideal, its extension, of course, that is an ideal, okay, of the codomain. But in this case, its extension of I via this map looks like this. Okay. Then the second one, it says that every ideal of S inverse R looks like S inverse I for some ideal I of. Okay, so this answers this question that an ideal of S inverse R, this ring of fractions, how does it look like? So it looks like S inverse I for some ideal of R. So what is S inverse I? It is just this one. This numerator, it is coming from I, and this denominator, of course, it is coming from S. Okay, and then this third one, it says that this S inverse I, this improper ideal provided. So it is if and only if this I intersect with S. Okay, so this intersection is non-empty. You can verify that. So can anyone give a quick proof of this one? Let me know whether you are following or not. Yeah. So let's say you have a common element S belongs to I intersection S. Then can you verify that this thing is improper ideal, or in particular this ideal it contains the identity element? So you can verify that. What about S by S? This is an element of S inverse I, right? And this is the identity element. So yeah, this is 1 by 1, and this proves that S inverse I, it is same as S inverse R. In fact, this converse also you can prove that whenever this thing is improper ideal, means it contains the identity element 1 by 1, then uh, yeah, so you can verify that this intersection is non-empty in that case. So 1 by 1 you can just write A by S, where A is coming from I and S is coming from S, and then just use the so these two, so they are same equivalence classes. So then you use that equivalence relation to prove that this I and S, they have a common element. Is it fine? Okay. And this 4, it says that there is 1 components between prime ideals of S inverse R and prime ideals of R that don't meet S. Okay. So in other words, here if P is a prime ideal of R such that P intersection S is empty, then S inverse P. This is the prime ideal of S inverse R. Okay. In fact, this is only. Okay. So any ideal of S inverse R, it looks like S inverse P for some ideal P, and this is a prime ideal if and only if this I, this is a prime ideal of R which don't meet this S or does not intersect with S. Okay. Okay. Now let's see how we can generalize this notion of ring of fractions to module of fractions, and then we will see some applications of these localizations. Okay. So this is. Let me know if you have any question. The formation of module of fractions from an R module M and a multiplicatively closed subset S of R. So basically same thing. Let's just write it quickly. Define a relation on this Cartesian product M cross S. Right. So here first component is coming from M, and again second component is coming from S. It is equal to Y times Y comma T if and only same definition. So U times T times X times Y, that is equal to 0 for some M belongs to S. So I think all of you are familiar with modules, right? So it is generalized version of a vector space. So here it is built over an arbitrary ring R. Okay, and you have two operations here in module. So one is just addition. So whenever you have two elements of this module, you can add them. What you get, that is another element of this module. And you have scalar multiplication, where scalars are coming from R. Okay, whenever you have an element of R and you have an element of, so this an element of M and this an element of R, so you can multiply them. What you get, this product, that is an element of M. Okay, so and this scalar multiplication and this addition, they satisfy certain certain properties, and in that way we define what is module. Okay, so you have a commutative ring with identity and you have a multiplicatively closed subset F, and how can you form a module on S inverse R? So this is the way. So you first define this relation on this ordered pair, okay, in this way, and then again you can verify that this is an equivalence relation. This is an equivalence relation, and of course you denote, okay, this equivalence class by this way, x by s, and then what is S inverse M? It is collection of all these equivalence classes. Okay, so this is here, and then now you can give an S inverse R module structure on S inverse M by defining, of course you should define this addition in this obvious way, T times X plus S times Y. So x and y are elements of M, and you are multiplying it with these scalars T and S. They are coming from R. So it makes sense. So this is an element of M, and in the numerator you have S times T. Okay, and you have, so whenever you have this an element, so of course you cannot multiply two elements of S inverse M, right? So you take one element from S inverse R and another element from X in X by S, that is an element of S inverse M. So then you can multiply them. So it is X times US. So here for all X by S, Y by T belongs to S inverse M, and this A by U belongs to S inverse R. Okay. Now you can verify that this, okay, this S inverse M, this is, okay, so I should, so this is called modulo fractions of M at S, or this called in the localization of M at this multiplicative closed subset. Okay, now so I should ask that can you consider S inverse M as a module over R? Yes. Can you consider? Yes or no? So of course S inverse M is a module over S inverse R. So now this S inverse, okay, this S inverse M, this can also be regarded as an R module. Okay, so you have addition here. Now how can you define scalar multiplication where scalars are coming from R? Yes. Can anyone answer? So you can consider S inverse M this an R module via this map A from R to S inverse R. So here A goes to A by 1. Okay, so you consider an element of R and you consider an element of, so this is an element of S inverse M, this is an element of R. How can you define an element of S inverse M? Yes. So A you can think A by 1, right? It is Ax by S. Is it? So you can consider S inverse M, that is also an R module. And now that, what about this natural map? The natural map, let me denote it by big F. This is from M to S inverse M. So both M and S inverse M are R modules. Okay. So if you define this natural map, X goes to X by 1, what can you say about this map? Is it an R module homomorphism? Can anyone answer this? Is it an R module homomorphism? Yes. Okay. So this is an R module homomorphism. One can verify that it preserves not only addition but also scalar multiplication, where scalars are coming from R. Okay. Now I think enough terminologies or notations. So now let's see some applications of localization. And okay, so before that, I should record this this proposition. but at least for rings I can okay, so let me first give this proposition and then we'll discuss. Okay, so this is right, the process of localization. This can be considered as functor. So the localization is exact. What I mean that whenever if this is phi and this is psi, it will be an exact sequence of R modules. What I mean by exact sequence, so here this is a sequence of two R module homomorphisms, phi and psi. Okay, we write in this way that phi is a R module homomorphism from L to M, and psi is an R module homomorphism from M to N, such that this kernel of psi. Okay, so this that is kernel psi, that is same as image of phi. So whenever you have this condition, then this kind of sequence we call it exact sequence. Okay, and it is very useful in homological algebra. Okay, so whenever this is an exact sequence of R modules, then you can just localize with respect to this multiplicatively closed subset S. So here first let me consider a multiplicatively closed subset of R. Okay, and then you localize this. So this is S inverse L and S inverse M, S inverse N. What about this math? So for phi, can you have, let me denote it by S inverse phi and S inverse psi. Okay, where okay, where this S inverse phi, this is the map. Okay, from S inverse L to S inverse M. How can we define this? Let's consider one element of S inverse L. How can you map it to an element of S inverse M? By using the map phi, can you define? Can you define? So here L is an element of L, right? And you have this map from L to M. So you can just apply phi on L. You can get an element of M, right? And you just in the denominator you just you just write S. So you can verify that this map, this is an S inverse R module homomorphism. So not only it preserves addition, but also scalar multiplication where scalars are coming from S inverse R. So this is an R module homomorphism, S inverse R module homomorphism. This also S inverse R module homomorphism. Now one may ask whether this sequence is also exact or not. What I mean that yeah. So this thing, then this is also an exact sequence of S inverse R module. Yeah. So this is also an exact sequence of S inverse R modules and S inverse R module homomorphisms. So what I mean that this kernel of this map, okay, let me write it. That is this kernel of S inverse psi, that is same as image of S inverse phi. Okay, and some consequences of this. So as consequences, we can verify these things. Okay, so in homological algebra or in commutative algebra, sometimes we need to verify whether certain sequence is exact or not. Okay, so in this way, we can reduce it to the local case. What I mean that okay, so these properties we call local properties. Okay, so let me first define this one, that the property of module respectively modules or respectively rings is called a local property if if it is characterized on local rings. Okay, so what I mean that let's see some properties that okay, so let me state that okay, so this is importance of localizations and how we can reduce any problem to a local problem. So what I mean that you can just reduce it to local rings, and over local rings we have many nice theory we can use that. So for example, you have this proposition that so you consider an R module M, then you want to verify whether this module is 0 or not. Okay, so this one is 0 or not. So I say that I claim that this is equivalent to say that M localized at P. What I mean that this is just S inverse M, where S is just R minus P. Okay, so this one is 0. For every P belongs to spec of R. Okay, and this is equivalent to say that M localized at every maximal ideal, that is also 0 for every M belongs to X of R. Okay, so this is one proposition. Another proposition you can have, so suppose you have a module homomorphism. So let's say consider for an R module homomorphism, let's denote this by phi from M to N. Again, the following are equivalent. So suppose you want to verify whether this map is injective or not. This R module homomorphism, this is injective or not. So it's enough to verify it locally. What I mean that you can just consider this map M localized at P and N localized at P. How do you define this map? So X by S, it goes to phi of X by S. Okay. Yeah. So this is for all X belongs to M and S belongs to M. Yeah. So this is injective for respect of R. And you have this third one that is just localized at every maximal ideal. Then also you have this condition that this is injective. So it's enough to verify this property, this injectiveness of this map locally. Okay, so in that sense, this property of injectiveness of an R module homomorphism, it is local property. Okay, so this being zero, this property, it is also local property. Okay, so this is injective for okay for every maximal ideal of R, and similarly you can verify that. So respectively, surjectiveness. Okay. So being this injectiveness of a module homomorphism or surjectiveness of a module homomorphism, all are local properties. Is it fine? Yeah. And something more, we have that okay properties of rings which are local properties. So to verify, so okay, so for example, this one that this ideal containment. So all this problem has real life application. So this ideal containment uh, problem. So this is also a local property. Okay. So what I mean by that, yeah. So you consider. Okay. So this is first one. Okay. So for two ideals I and j, you want to verify whether one is contained in another or not. So in general, it is very difficult. It is very difficult to verify this. Okay. So at least you can reduce this problem to a local commutative local ring with identity. Okay. And then you can use many nice theory over local rings to verify this containment relation. Okay. So this I is contained in J if and only if I localized at P that is contained in J localized at P. So of course here I and J both you can consider as R modules, right? So of course this localization it makes sense, or you can verify or you can consider it as in this way. So it is nothing but S inverse J. What is S? It is just R minus P. Is it fine? Yeah. So you have this containment in R localized at P for every prime ideal of R P. Okay. So this is one example. Another one is being reduced in reduced ring. This is also a local property. Okay. Okay. So what I mean that so what is this uh, reduced ring? Can anyone recall what is reduced ring? That is the ring that it has no non-zero nilpotent element. Okay, so here R is reduced, we can only, this is, so for every P belongs to spec of R. And why this over local rings? Life is easy. Let's see at least one lemma that is useful in local ring, and we have that. So it is we call it Nakayama lemma. Okay. What is that? So here, so this is finally generated module over a commutative local ring. Okay, over a local ring R, and then okay, so and what is local ring? Which has, okay, so let me first define what is local ring, and then how it is related to localization. I'll explain. So this local ring is nothing but okay, okay, that is R has the unique. So a local ring is nothing but a ring with the unique maximal ideal. So a commutative ring with identity, it has at least one maximal ideal, right? That you have done in the ring theory course, right? So now when your ring has only one maximal ideal, then that ring we call it local ring. Okay. So this R has the unique maximal ideal. Okay. And this maximal ideal, let's denote this maximal ideal by M. Okay. Then you have two statements that if you consider any proper ideal, so this is proper ideal, and this I times M. Okay, so any element of this, how does it look like? It is a finite sum of this kind of element, ai times xi. This finite sum where ai is coming from that ideal I and xi is coming from M. So you can verify this, then that this is an R submodule of M. So when this R submodule it is same as M, then you can conclude for ring where I is a proper ideal, then you can conclude that this M is 0. Okay. So in many cases we need to verify whether certain module is 0 or not. Okay. So at least over local ring we can use this lemma to verify whether a module is 0 or not. And because of this proposition, we can reduce it to first local case. How? Because for any commutative ring with identity, if you just localize it at P, then we get a local ring. So we should somewhere we should state that. Okay, so I think in the example, yeah. So this thing, the here I should state this. So this is yeah. Okay. So here I can. This is exercise. Exercise. I can state this that verify that are localized at P. This is a local ring, or it has what I mean that it has the unique maximal ideal, namely it is PRP. Okay, what is that? So it is A by S, where A is coming from P and S it is outside P. Okay, so you can verify that this is a maximal ideal, and in fact this is the unique maximal ideal of this ring. So in that way, so that is R localized at P is a local ring. Okay, so this justifies that why we call it localization. Okay, so this is one instance, and we will see other examples that why and other justification that why we call it localization. Okay, yeah. So we will say talking about this Nakayama lemma, and then you have second statement also that whenever this. Okay, so suppose you have this general problem that you have a module and you want to, it is given that it is finally generated, okay, and you want to find a generating set of that module, okay. So you can find that generating set in this way, that you just consider this quotient module m mod this maximal ideal times m. You can verify that this is a vector space. This is a vector space over R mod m, and you want to okay, so you want to find a generating set of m or a minimal generating set of m. Okay, so how can you do that? So you just consider this vector space, and if m is finally generated, then this is also finally generated. Okay, so what you can do, you can find any generating set of these, and so then an element. Okay, so you just consider, let x1 xn belongs to m such that x1 bar, if you consider their equivalence classes in this quotient module, suppose m mod mm, okay, then these representatives x1 up to xn will generate m. Okay, and when this collection, it is a basis, so this is a vector space over this field. So m is the maximal ideal, right? So R mod m, this is a field, and this is a finite dimensional vector space of this. So you can find a basis. So you consider, so suppose this forms a basis of this vector space, then x1 up to xn, it gives a minimal generating set of m, in the sense that you cannot reduce this set to get a generating set of m further. So you cannot reduce this set further. So in other words, if you just omit one of these elements from this set, then it is no longer a generating set. Is it fine? Is it fine? Okay, so now let's see why. So I'll take 3 minutes more. I have 3 minutes more. So I'll explain why do we call localization. Okay, so this term localization, it originates to study geometric and topological objects locally. So that is their behavior near each point. So let's consider algebraic geometry and some basic stuff. Okay, so in algebraic geometry, this in algebraic geometry, uh, often we consider this an affine algebraic set this is nothing but V. This is a subset of k power n. So here K is a field. I should consider algebraically closed field. Okay. Okay, so you don't always need this algebraically closed field, okay, but we are assuming this to explain what is Hilbert-Null-Strangers and all. So K is algebraically closed field, and here n, this is some positive integer, okay. Yeah, and V is a subset of k power n. And what is V? What I mean by affine algebraic set? So it is just zero set of some collection of polynomials. Okay, some collections of polynomials. This one. Let's say it is Fr or Fm. Okay. So this kind of subset, we call it affine algebraic set. So this kind of set, it can be, this can be identified with a ring, namely this is quotient ring of a polynomial ring. So you consider same number of variables, and there is a polynomial ring in x1 up to xn. These are variables, n many variables, and there is a polynomial ring over k, and then you consider ideal of V, and you just take quotient ring. Okay, so in this way, in one side you have affine algebraic set, that is V is a subset of k power n, and in other side you have coordinate rings. So this is just, we denote it by gamma of V, so it is just this quotient ring. Okay, K polynomial ring in x1 up to xn modulo I of V. Okay, so when your field is yeah, so there is a one-to-one correspondence, and this is just it is nothing but the name is Hilbert-Null-Strangers. And so there is a one-to-one correspondence between points with maximal ideal. Okay, so here, namely, if you consider a point in P, so this is okay. This is nothing but an n tuple. This is a point in V, then its image. So the corresponding maximal ideal, it is nothing but x1 minus a1 xn minus an. Okay, where this small xi, it is just equivalence class of big xi here. Okay, yeah, and you can verify that this is a maximal ideal in this coordinate tree. Okay, now so this is the main thing, the behavior. So in algebraic geometry, sometimes we want to study the behavior of an affine algebraic set. So what is that? It is just basically zero set of some collection of polynomials, right? If you just consider one polynomial or one curve, so it's zero set, it gives a curve, right? And sometimes we want to study the behavior of that curve in a particular point. So the behavior of this algebraic set V at a point at point A, it can be observed by studying the local ring. So you consider this coordinate ring, and so corresponding to this point A, you have this maximal ideal. You just localize this coordinate ring at that maximal ideal. Okay, so many properties of this algebraic set or If you consider a curve like this, so many properties of this curve, it can be studied locally. So you consider a fixed point, and corresponding to this point, you have a maximal ideal, and that coordinate ring you just localize at that maximal ideal. So the behavior of this algebraic set, it can be studied by studying this local ring. Okay, so so that is why we call it localization. So it is actually reducing every problem to local problems. Okay, I think that's all. I should stop now.